In this video, we will start translating some more complicated sentences from SL into QL. Here's a symbolization key. Let BX be X is a badger. CX means X is a cat. MX means X is a mammal. RX means X is a reptile. SX means X is a snake. Little t names Tibbles. However, there's something missing. Remember that we don't have a symbolization key for QL until we've specified a universe of discourse. Here, our UD will be animals. That means quantifiers range over animals. For all X means every animal, and exists X means for some animal. Consider this sentence. If Tibbles is neither a badger nor a cat, then Tibbles is not a mammal. In QL, we have all the same sentential connectives we had in SL, and symbolizing a sentence like this mostly just relies on the skills we developed translating into SL. Neither nor has two natural translations, so we might translate this sentence in two different ways. One way is not, parentheses, BT or CT, close parentheses, arrow, not MT. The other is parentheses, not BT and not CT, close parentheses, arrow, not MT. Now consider this sentence. Not every animal is a mammal. For all already means every animal, because our universe of discourse is animals. So this becomes not for all X, MX. This means it's not the case that every animal is a mammal. Now consider this sentence. Every cat is a mammal. The universal quantifier always talks about everything in the universe of discourse. With this symbolization key, that means every animal. So how can we talk about cats in particular? We do this by writing for all X, CX, arrow, MX. This means that for every animal, if that animal is a cat, then that animal is a mammal. This is a general pattern that we'll use again and again in translating into QL, when we want to say that everything which has one property also has another property. For a sentence of the form, every this is a that, or a sentence of the form, all this are that, we translate it using a universal quantifier for all X and a conditional. So we say, for all X, if X is a this, then X is a that. Here are some examples of that pattern. We've already seen every cat is a mammal, which we translate as for all X, CX, arrow, MX. All badgers are mammals. For all X, BX, arrow, MX. All snakes are reptiles. For all X, SX, arrow, RX. Note that it's possible to write this sentence for all X, CX, and MX. However, it doesn't say that every cat is a mammal. This is a sentence of QL, but what it means is that every animal is both a cat and a mammal. And if you think about it, that sentence means something. It's just false. There are plenty of animals that aren't cats or that aren't even mammals. So it's important to distinguish between the pattern we saw earlier that uses the conditional inside the scope of a universal quantifier and this pattern that uses a conjunction. Now consider this sentence. Some mammals are cats. We can translate this with an existential quantifier, exists X, MX, and CX. This means that there is some animal which has the feature both of being a mammal and a cat. This is another general pattern that we'll use again and again. It allows us to say that there are things which have one property and which also have another property. Some this or that is schematically translated as exists X, X is a this, and X is a that. That is, we use an existential quantifier and a conjunction. Here are some examples of that pattern. Some mammals are cats. Exists X, MX, and CX. Some mammals are badgers. Exists X, MX, and BX. Some reptiles are snakes. Exists X, RX, and SX. Although there's technically a sentence of QL that looks like this, it's not a clear translation of any English sentence. So I'm just going to put a red X over it. Don't write an arrow inside the scope of an existential quantifier. In general, it just won't mean what you want it to mean. Don't do it. Now consider this sentence. Not all mammals are cats. There are two ways to think about it. The first way to think about it is it's not the case that all mammals are cats. So you put a negation at the front, and then you use the universal quantifier and our translation for all mammals are cats. You get not for all X, MX, arrow, CX. Another way to think about it is as saying that there's some mammal which isn't a cat. There we'll use an existential quantifier. There exists X, MX, and not CX. Importantly, the two different translations use different quantifiers, different connectives inside the parentheses, and they put the negations in different places. But they're logically equivalent, so they're equally good. So the general pattern, not all this or that, not everything that has one property has this other property, can be translated in two different ways. Not for all X, X is a this, arrow, X is a that, or exists X, X is a this, and not X is a that. Now consider the sentence, no snakes are mammals. Again, there are two ways to think about it. If you think about it using a universal quantifier, it's saying for every animal, if it's a snake, then it's not a mammal. For all X, SX, arrow, not MX. If you think about it in existential terms, it's saying that there doesn't exist a snake mammal. So does not exist X, SX, and MX. Again, these are equivalent translations, so they're both right answers. But they use different quantifiers, different connectives, and they put negation in different places. Here's the general patterns. If you want to say that nothing which has one property has a second property, no this is a that, you can do it with a universal quantifier for all X. If X is a this, then not X is a that. Or you can do it with an existential quantifier. There does not exist an X such that X is a this and X is a that. Note that the properties which we connect together don't need to be single predicate letters. Consider, for example, this sentence. No mammal is both a cat and a badger. Here it's a no this is that pattern. This is a mammal, and that's both a cat and a badger. So we translate using the same structures, even though both a cat and a badger requires a couple of different predicates held together on its own. Using the universal quantifier, we write for all X, MX, arrow, not, CX and BX. Using the existential quantifier, we write there does not exist an X, mx, and cx and bx. In this video, we've introduced translating sentences that relate one property to another. And we've learned 4 general patterns. Here are how those patterns are represented in the textbook. The bottom of this slide is just copied from the reference tables at the back of the book. You should feel free to look at this while working through practice problems, because you should become comfortable with these patterns and learn to use them in translating.